this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on Markov chains. So we looked at the mathematics behind them and setting them up in a previous lesson. Now we're just looking at classifying states, which is very important when solving problems. So we have a Markov chain on your screen with 5 states. So we're going to define this operator here. So it's a binary operator. It needs 2 things to operate on. So we say that 2 states communicate with each other if either one can be reached from the other in a finite number of steps. So let's look at our Markov chain and see which states communicate with each other. So clearly 1 and 2 communicate with each other. You can get from one of those states to the other in one step. Now 1 also communicates with 4, for example. We have that you can get to 4 if you start at 1, you just go 1, 2, 4. You can also get to 1 if you start at 4 by going 4, 3, 1. So they communicate with each other. So it turns out that 1, 2, 3, and 4, each of those states communicates with each other state. Now it turns out that 5 doesn't communicate. So 5 is what we call an absorbing state. We saw them in the previous lesson. So that's a state in which if you go to it, you stay there forever. So 5 actually doesn't communicate with any of the other states, because if you're in state 5, you can't get to any of those other steps. So 1, 2, 3, and 4 all communicate with each other, but 5 doesn't communicate with them at all. So this gives rise to us. We can make the chain a little simpler by dividing things into classes, dividing things into groups, and each thing in the same group communicates with everything else. So for our Markov chain here, we're going to divide it into 2 groups. So the first group is going to contain the states 1, 2, 3, 4, and the next one will contain state 5. So this class is the class containing 1, 2, 3, or 4. So you can write it as 1 like this, class containing 1, or class containing 2, 3, 4, or whatever. Write the second class as this, the class containing 5. So if you have elements in the same class, then they communicate with each other. Elements in a different class do not communicate with them. So you can't have 2 elements in different classes that communicate with each other. So if you can do what we just did and divide the chain into communication classes, what we do is we call the chain reducible. And obviously, if there's only one communication class, which means every state communicates with every other state, we call it irreducible. So what we might do to make things simpler, we might actually divide this into sort of 2 kind of states. So I'm just going to call A to represent this group here. So what we want to do, we need to be able to classify states as either transient or recurrent. State is said to be recurrent if any time you're in that state, you can be sure that you will return to that state. And if that's not true, if you're in a state but there's no guarantee you'll return to the state, then that state is transient. So let's look at our Markov chain. It turns out that 5 is recurrent. So I'm going to put an R there. So if you're in state 5, you're going to stay there. So you're going to stay there the next time and the time after that and so on. It turns out all of these states here, 1, 2, 3, 4, are transient. So the reason is that if you're in any of those states, you may end up going to state 5 and never return. So if you're in state 4, you might go to state 3, then state 1, then state 2, then state 5. And if you get in state 5, you'll never return. So it turns out that if you have a communication class, either all states will be transient or all states will be recurrent. So 5 is this state here was recurrent, so that means 5 is a recurrent class, and this class here containing 1, 2, 3, and 4, that's a transient class. So you can't ever have a situation in which there are 2 states in a communication class where one is transient and one is recurrent. Doesn't work like that. If a state is transient and another state is recurrent, there's no way they can be in the same communication class. So one thing to note, it turns out that any absorbing state is always recurrent. But the converse isn't true. You can have a recurrent state that is not absorbing. So it turns out that these definitions have very important ramifications. So for example, we know that if a chain is irreducible, so there's only one communication class, and it's aperiodic, it will always have a steady state distribution. We won't get situations like we had in the previous lesson where there were two absorbing states and you have two sort of steady state vectors. So that's what we'll be looking at in this lesson. All right, thank you so much for watching this video. This has been the luckiest maths teacher in the world. Have a great day.